Hello again, everybody. This video is for assignment 2. Like all the other videos before this, or the video before this, and videos afterwards, this is not necessarily meant to solve these questions for you or tell you exactly how to solve them, but just kind of how to clear things up and any kind of tips or tricks I can give to you without just giving you the answer. So I'm going to try to make this a short video, but there's 5 questions and they're all a little bit more in depth this time. Like I said at the beginning of the semester, and as I'll say throughout all the semester, is I hope you're not waiting to do this or watching this video when the assignments due very quickly. It's good to get this stuff done ahead of time, or at least start working on it ahead of time, because it might take you a little bit longer. So let's kind of go through this. Remember, for all of this math in this class, your final answer should always be in 3 significant figures, and all units or all answers should be in metric, so that's going to be in meters per second squared, anything unless it's otherwise indicated. So let's go through this assignment. First question says D went for a 10-kilometer run and completed in 65 minutes. She displaces from her start point by 30.5 kilometers. So this is kind of your first real introduction and the difference between speed and velocity, or distance and displacement. Remember, if we're looking at, I'm going to draw all over this document, so hopefully it's not too confusing. But if we're looking at somebody running a race and they're kind of start here and end here, and they're kind of going all over the place like this, they make circles and like that, and they eventually get to their end there, that entire path is their distance. However, let's see if I can change the color of my pen. This might be easier just using my mouse. If we're looking at displacement, though, we're looking at from one point to another. Okay, this straight line is our displacement. Generally, we say that displacement, we will use like a small case. I do apologize, my pen just doesn't work. I think my pen works fine. It's just my computer's, the touchscreen is not great on it. But we say displacement, we use small case d, and then just for the sake of consistency, we'll change the color again. Distance, we use a capital D. Okay, so let's take another look at this. We'll get rid of all this nonsense on the screen. So I'm asking you for her average speed. Now realize too that I gave you the run, I gave you in kilometers, and I gave you her time in minutes. So you probably should do some conversion for these. Once again, I'd suggest solving and then converting. It won't matter too much for this type of question, but it's just a good habit to get into beforehand. And then once again, if you're looking for equations, you can either go through the lecture or go to one of the cheat sheets that's available on Canvas. But if we're looking at speed, remember that speed is simply distance divided by time, not displacement. Displacement divided by time is velocity. For B, this one might be a bit tricky because I'm not sure how well I covered it at this point, but I'm telling you, based on the answer you got from A, not the one you rounded up to 3 significant figures, but your intermediate answer, and given that her stride length is 0.75 meters, what would her approximate stride rate be? This is something, once again, at this point in time, I'm not sure. I probably did, but I'm recording these ahead of time. I'm not quite sure if I covered stride rate and stride frequency and like that. So I will just kind of give you the equation for this. But generally, if we're looking at running, walking, anything like that, sort of bilateral, or not bilateral, bipedal locomotion, so gait, running gait, anything like that, is generally we say that speed is equal to our stride length, so SL for stride length, multiplied by stride rate. S for stride, R for rate. Okay, so it's just a multiplication problem. So you already calculated speed, and I gave you stride length, so now you have to figure out your stride rate. And it just takes some clever isolation to figure out, to isolate a variable to figure out the answer. So I'm going to get rid of all this nonsense again. So let's go to question 2. So it says Frank ran a 1,000-meter race in 4 minutes and 7 seconds. For the first half of the race, his velocity was 5.7 meters per second. For the second half of the race, his velocity was 2.57 meters per second. What is his acceleration? Now, this seems like a bigger question than it really is. But, and this is also kind of introducing to you, which you'll see in some questions as well, is you don't need to use every number that's given you. These are concept questions. It's testing or looking to see if you understand the concept of these things. So it would help to understand the concept of acceleration. Acceleration is simply the change in velocity over time. That's why we say that acceleration, acceleration is meters per second, or we also see it written like this, meters per second to the -2. Okay, what we're really looking at is we're looking at how velocity right here, because velocity is in meters per second, changes over time. So if we take a look at the equation for acceleration, we see that acceleration is equal to the change in velocity over time, sometimes change in time. And we know to calculate a change, we look at either the second or sometimes you hear final velocity. I'm just going to put 2 for second. Sometimes you hear final instead, minus the initial or first velocity. This will give you a change in velocity. Now you have to figure out what was the time this all occurred in. Well, I already gave that to you somewhere in here. I gave it to you right here, 4 minutes and 7 seconds. Maybe you should convert 4 minutes and 7 seconds to seconds total. Now you're going to look at this and tell me whether their acceleration was positive, negative, was it 0? We went over this in the lecture of what acceleration means. But generally, if you're looking at acceleration, if acceleration is positive, we're seeing that velocity increases. If velocity is net, or if acceleration is negative, we're seeing a decrease in velocity. Or we can look at the changes in direction. If they're both going in a positive direction, we have a positive increase. If one's in positive, one's in negative, we can have negative increase, negative decrease. That's kind of the table that I tried to get you guys to draw when you're looking at this stuff. So if we have a positive and negative, we have a positive acceleration. If we have a negative and negative, we have a negative acceleration. If we have a positive and a negative velocity, we have a negative acceleration, and vice versa. If we have a negative and a positive, we still have negative. Okay. And then, you know, what does it mean if acceleration is 0? So our next one, number 3. Charlie decides to swim in open water. Charlie swims at a velocity of 0.92 meters per second, but because of the current, he ends up displaced by 36 degrees to the right from his start point. What is his resultant velocity? This should be, I think, in the linear kinematics presentation around slide 21. It might be 20 or 22. I think it's around 21. But this is kind of a classic solve the triangle question. So I'm not going to get too much into this, but I will give you this. We can just simply draw a picture. Drawing a picture always helps. And in fact, what I would suggest for every kind of, you have to turn in your work anyways for all these assignments, but draw out the situation. It might help you think a bit more. So that's what I'm going to do. I'm going to say, this is Charlie swimming across the river, this arrow right here. And he's swimming at, what was it? 0.92 meters per second. But the current displaces him by 36 degrees to the right. So it's really swimming like this because the current is pulling him to the right. So this is 36 degrees. So right here, we have a right triangle. We know this one. We'll say that this is the adjacent side. This is the adjacent side. This is the opposite side. And this is the hypotenuse. So you've got the adjacent side, you've got theta. You don't have the opposite side, and you need to figure out the hypotenuse. So this is where you're going to go to your trigonometry rules. So you have to ask yourself, am I going to use sine, cosine, or tangent here? Let's go to number 4. Number 4, Mac takes a free kick in his soccer match. Just before his kick, he flexes his knee to 34 degrees. He then extends his knee to 156 degrees upon contact with the ball and does so in 0.48 seconds. What is the angular velocity of his lower leg during knee extension in radians per second? So as we went through the angular kinematic stuff, is you can measure angular velocity in degrees per second. But, you know, if we were to keep going and we want to convert something to linear motion, we have to convert our angles from degrees to radians. And remember that for every radian, there is 57.3 degrees. So what I'm really asking you for is, there's another little dot there, is this equation. This is angular velocity, and it is equal to our angular displacement, so change in theta over time. So you've got everything you need here, but you have to figure out, okay, what's the change in theta? When we looked at kind of our displacement, that is, you know, V2 minus V1, D2 minus D1, theta 2 minus theta 1. But you need it in radians per second. So if, remember that there are 57.3 degrees for every radian. So I'd suggest possibly converting it up front here. These questions aren't meant to be too tricky. So number 5 is probably one of the more tricky. Speaking of which, number 5 is probably the most tricky question you'll ever experience in this class. It's not meant to be tricky, but it might be the most tricky you'll get in this class. But it is important because it may be on an exam in the near future. But it says Dennis is up to bat during her. It says her, it should be his. That is weird. It's not weird. He can call himself whatever he wants. But I'll fix that later. This typo. But during his bat, always hear this, is 263 degrees. During his bat, he swings his bat, 263 degrees in 0.65 seconds before contacting the ball. He makes contact with the ball 58 centimeters down the bat away from the axis of rotation. What is the linear velocity of the ball after contact with the bat? So this is something we talked about in our angular and linear kinematics, and this equation is on the cheat sheet, I think, for the second and third exam. I think you can find this. But if we're converting angular velocity to linear velocity, we say that the linear velocity is equal to the angular velocity multiplied by a radius, the radius of that swing. I gave it to you right here, 58 centimeters. Important things to consider is I gave it to you in centimeters. We use meters. I gave you essentially as angular displacement, but I gave it to you in degrees, and we're converting linear, or we're converting angular velocity to linear velocity. So you should probably convert your linear or your angular displacement in degrees to radians. And then remember that omega right here is simply change in displacement over time. So this should help you guys with all of these questions as normal. If you get stuck, you have questions, something's not clear, feel free to email me or get a hold of me on Slack. I hope this helped, and goodbye.